Okay, so let's dive in. The first problem is on the screen. So we have an electron. It's released, we're told, a distance of 1 centimeter from the surface of a charged hollow sphere with a diameter of 20 centimeters. We're told that the speed of the electron once it reaches a meter from the surface of the sphere, it ends up being 50 kilometers per second. If that's the case, we're asked what is the surface charge density on the sphere. So let's quickly draw a picture here to have a better sense of what's going on. We have a large hollow sphere. I'll just kind of give it a little dashed kind of inner perimeter here just to indicate that it's hollow. Let's switch to red maybe. We've got an electron that starts pretty close, 1 centimeters, pretty small distance, and then sometime later it's released. And we're told that it starts out at 1 centimeter, it goes to a meter, so it's obviously moving away. From that, we can conclude that there's some repulsion or something like that going on. So let's just label a couple of these distances. The initial distance, the final distance. And these are, like we said, 1 centimeter and 1 meter respectively. I'm not going to really probably deal with the numbers. We'll just solve this in variables and leave the actual numeric computations up to you guys. The sphere we have here has some sort of radius that we'll denote with capital R. And I think the only thing that we need to label here otherwise for a pretty complete picture is that the initial velocity here is 0 and the initial or speed here is greater than 0, specifically 50 kilometers per second. But the key difference is that the speed here is non-zero. So it's picked up some kinetic energy is the main point. The other thing that we should keep in mind, and I think this might be actually going ahead of what you guys have seen in lecture, maybe it's not. From the outside here, you guys have learned this already for electric fields, but the electric potential, whether it's a hollow sphere, if it's a solid sphere, your potential outside of this sphere is such that any other charge that you put near it, for instance, our electron, that's the red dot here, it looks like a point charge as long as you're outside the sphere. If you're inside the sphere, something else totally different happens. You have to kind of use some tools that I don't think you guys have yet or may not acquire in this course. So let's just complete this thought here. So the electric potential outside the sphere looks like the potential from a point charge. And let's call that point charge, let's say it has some amount of charge, capital Q. And what that really means is, to connect this to what we're looking for, the surface charge density, we call this sigma, as is convention. Imagine you have a charge Q and you distribute it over the surface of this sphere. So sigma is the amount of charge per unit area. So if you have charge Q, the area of a sphere is 4 pi r squared, just the surface area there. So that's what sigma is. We'll sub this in later. We might sub it in as a more, something like this, in this form. But with that in mind, we can kind of get underway. And the way we can describe the problem to start solving it is initially here. The kinetic energy is 0. This is implied by the fact that the velocity is 0, but we have some potential energy, some electrical potential energy. There's a repulsion between the big sphere and the electron. So when released, kind of that potential energy gets traded in for kinetic energy. So we have some kinetic energy here later on. And as is typical, I think if you guys remember, previous topics, maybe last semester, talking about potential energy, we can define where our zero is in potential energy, because what we're concerned with is changes. So I'm going to say that this is our 0 point here, potential energy. So we'll say that we've traded in some amount of potential energy, and that's been converted into kinetic energy. That's really just a statement of conservation of energy, which we can kind of write like this. Change in kinetic energy plus the change in potential energy has to equal to 0, because if we're considering the system that is the big sphere and the electron, there's no external input of energy. So the change in kinetic energy is just equal to half mv squared, or mvf squared if we prefer, plus 0. This is the first term because we initially have 0 kinetic energy. And right now I'll just maybe write potential energy final minus potential energy initial. And that has to equal 0. The reason I'm doing it like this is because I don't know if you guys have seen what the potential energy, actually no, you should have seen what the potential energy is between two point charges. So scratch that. Let's do this in one line. So like I said, we're just pretending that this big sphere is a point charge because the electron that's interacting with it is outside. If it was inside, it'd be a totally different story, but we can do this in this case. So we have potential energy is 1 over 4 pi epsilon naught, same constant as we're familiar with. We have the charge of the electron, the charge of the sphere, and the distance between the two of them. So if we're doing final minus initial, we have df, and then we're subtracting from that kind of the initial condition. So it looks pretty similar. We just have a different separation between the two of them. Does this make sense as we've written it? Good time to pause and kind of make a check. df, which is a number that's in the denominator of this fraction, the final distance is a big number, so this term will be smaller. The first term in this parenthesis set is smaller. di is a small number, it's in the denominator. The second term is going to be bigger, so a small number minus a big number is going to give a negative number. This means that our change in potential energy is going to be negative. That makes sense, we're moving farther from this kind of big sphere. And conservation of energy says if we've gained kinetic energy, it has to come from somewhere. So that corresponding increase in kinetic energy comes from the decrease in potential energy. So this is all good. And what we really want to get at here is this term sigma that we kind of talked about a second ago. That's wrapped up right now in this variable q. So what I'm going to do is we'll just do a bunch of algebra, fact a few things, and we're going to try and solve for q. Okay, so we don't need this 0 anymore. We have half mvf squared plus common to kind of all these is q over 4 pi epsilon naught 1 over df minus 1 over di. That's equal to 0. So now we need to get kind of q all on its own. So what we'll do is we'll multiply everything by 4 pi epsilon naught, divide everything by q. Okay, so we have, and maybe at the same time, we'll get rid of this guy. This is only 2. So instead of multiplying by 4 pi epsilon naught, we'll do 2 pi epsilon naught, but it will be the same. So we have 2 pi epsilon naught mv f squared divided by q plus capital Q. And what I'm going to do here, just to make our life a little bit easier, we'll kind of combine these two, and this will be lost my pen there. There we go. Lost my pen again. It'll be di minus df Is that correct? Yep, that is correct. So that equals 0. So now we can move this term on the right over to the right-hand side. Just recopy the first one, try and not get too sloppy on the penmanship. So that's going to be equal to q. And you might think I have to put a negative sign on the left of the Q here. What I'm going to do to take care of that is I'm going to switch the order of these two terms right here. So this will be df minus di divided by di df. So that should take care of a negative times what we had up here would have switched the order of these terms. And now all we need to do to solve for Q is say that Q is equal to the factor we had on the hand side, mv f squared divided by Q times di df divided by df minus di. So I think this is our answer. What I'm going to do just to make it as kind of final as possible, we had an electron was our little charge minus Q. That's the red right here. It's an electron. So Q is equal to minus E. E is also a positive number, remember. When we're talking about an electron, we give it a charge minus E. So this is our final answer. Hopefully not too difficult to understand how I got here, but what we're going to do, because this is an answer with a lot of terms, let's just pause for a second to make sure it makes sense and is something somewhat reasonable. So the first thing we want to check is the total sign on the whole thing. So right now we have a leading negative out front. That kind of, unless we have a negative from somewhere else, the final answer is going to be negative. So the only place where a negative can come from is the denominator of this second factor here. So we have df minus di. If we look at our diagram, df is further away from the sphere, or it's a bigger distance than di. So this denominator will come out positive. So the only negative here is this one right in the front. So the charge on the big sphere should be negative. What's going on here in terms of the physics, or what we're observing, is that the electron is repulsed by this large sphere. The electron carries a negative charge. For repulsion to occur, the large sphere has to have a charge of the same sign. So a negative is what we expect. So this is okay. The other thing that I've completely forgotten is that I said we wanted to solve for surface charge density. So this is really not very difficult, but I've omitted it. So maybe we're not as done as I thought we were. So to really satisfy the question, let's make the substitution that Q is equal to sigma times 4 pi r squared. And then do one more little bit of algebra before we're really done. Minus 2 pi epsilon naught mb subscript f squared divided by electron charge times di df over df minus di. Okay, so in other words, final answer minus, what do we have, epsilon naught mv f squared. The pi goes away, we have 2e r squared. Yep, di df. Okay, so I heard a chat notification. Let's go check on that. Yeah, is E short for, yeah, exactly. So E specifically means the number of coulombs that are carried by one electron. It is 1.6, it's either 609 or 602, something like that, times 10 to the minus 19. Yeah, so what I did at this step right here is I replaced Q with minus E, because we understand that this is just a positive constant. So this is for an electron. If we had a proton, which I'm just giving E and P, I hope you guys can follow. I think you can. We would say the charge is positive E. So E is just really a positive constant, just a number. We give it a sign independent of what that number is. We give the charge a sign. Okay, so yeah, we have sigma now. This is our final answer. The one thing I wanted to do is I wanted to do a quick unit analysis, because sometimes it's a little tricky with these. The results you get out of problems with electrostatics can be a little bit, they have a lot of terms, and some of the terms are a little weird. So to do the unit analysis, I'll make a note of something right here. The one that usually gives people trouble is epsilon naught, the vacuum permittivity, or whatever you guys want to call it. The value for our purposes right now doesn't really matter, but the units, usually when I write things in square brackets, I'm typically, context will tell you, but I'm typically describing the units. The units in this are seconds to the fourth, amperes to the second, which is a unit of current. Not sure if you guys have been exposed to that yet. Per kilogram per square meter. That's the units on that. Something you may have been exposed to is 1 coulomb is equal to 1 ampere second, but the SI unit system said that we use amperes, not coulombs or ampere seconds. So let's really quickly figure out what the units on this guy are. So we have epsilon naught, which we just wrote, so we'll copy it up above. We have mass, which is in units of kilograms. We have velocity squared, which is meters squared per second squared. The 2 doesn't have its E, which is the electron charge. That's the number of coulombs, but I already told you guys what a coulomb is in SI base units. It's an ampere second. We have radius squared, which is the same as meters squared, or that's the units of meters squared. And here we have this final term, this fraction. It's a length times a length divided by a length. So I'm just going to simplify that whole thing into a meter. And then we can hopefully simplify this whole thing and figure out if it makes sense. Okay, so I'm going to take care of those 2 meters squared. I'm going to take care of those 2 kilograms. Have I missed something already? I hope I haven't missed something already. All right, well, we'll keep going where I get to. I have a funny feeling that I've made a mistake somewhere, though. So this is per seconds on top. This becomes to the third. Scratch that second. This ampere becomes to the 3. I think I'm totally missing something. Oh, yeah, you're right. Thank you for catching that. Yeah, so in the chat, just got told it appears to the second. So my error was a copying error. Okay, so that's a really good catch. So instead of crossing off 4, we just have a 2 here. This is why having good handwriting is a excellent skill. So we just have that to the 1. I still think I'm missing something, so if people are catching that seconds here, which I kind of erased, we'll cross off delete an amp second. So this amp second here is like a unit of charge. So think of that as 1 coulomb. The problem I have is it's supposed to be coulombs per meter squared, and I have this extra meter hanging out that I haven't, I get per meter. So I think I've probably copied something wrong somewhere else. But what I'm left with is coulomb per meter, and what I'm looking for is coulomb meter squared. So I'm pretty sure the answer on the left here is correct when I've copied things, something else in the chat. Okay, cool. So I think Alex has us. If it's now the DFDI should be here in the top. Unfortunately, I wish it was that simple. So this is, if I really drew this out, we'd have meters squared divided by meters, which would equal a meter, which I included here. So I'm fairly confident in this answer here. It looks like what I have in my notes. It's the what I've done in the unit analysis. So I think this is getting drawn on. So what I'll do is I will proceed with the next two problems. They're pretty similar, and if we have time, we'll circle back, and maybe it'll give you guys a chance to spot my error, or maybe I'll have with a different view or take a second look at it. It will come to me. I just don't want to dwell on it too much, seeing as we're already 25-ish minutes in, and I'd rather get through these questions here. Cool. Okay, so that was the kind of electrical energy. Moving into just electric potential. And electric potential is kind of the really nice topic that I find starts to make this this unit look a little bit easier, because most things you can do with forces and electric fields, which are reliant on vectors and geometry a lot of the time, you can do with potentials. And potentials are a scalar function. So the complications of vectors are alleviated, which I think everyone agrees just makes it a little bit more simple. So we have a graph of electric potential that's filled out already. That's the top panel here in this figure. Part A of this question asks us to plot the signed electric field magnitude in the space provided. So the electric field is, if we were doing this with full tool set of calculus, vectors, and everything like that, is minus the gradient of the electric potential, where the electric potential is V, not the volume, not the speed. It's kind of complicated. It's usually a capital V. That is the electric potential. But for the case of what you guys are doing in this course and in this problem here, which is clearly a 1D problem, which is as a function of x, it's instead of this gradient, all this is the derivative. So we're going to take the derivative with respect to x of the potential. So what this is getting at, if you ever have a problem like this, the segments here, you have to figure out what the slope is, and then you flip the sign. So let's construct this graph. For instance, I'm just going to work from left to right. From x equals 0 to 1, the slope is obviously 0. So the derivative of something that is 0 is 0. Now in the second region, if you can see where my cursor is hovering, from x equals 1 to 2, the potential decreases, so decreases by an amount of 5 volts. So it's a delta V of 5, a delta X of 1. So minus 5 divided by 1 is minus 5. That's our slope. But don't forget, we need to put that minus sign in front. So actually, the electric field in that region is plus 5 volts per meter. And we can proceed similarly from x equals 2 to 3. The slope is 0. From x equals, what is this? This is 1, 2, 3, from 3 all the way to 6. The slope is positive 5 volts per meter. But because we have this negative, we can't forget the negative. It's super common for people, forget the negative. So slope of positive 5, including the negative, ends up being minus electric field minus 5 volts per meter. Here, from x equals 6 to 7, the slope is twice as steep and it's negative. So that means we have a slope electric field of positive 10. And then throughout the rest of the graph, it's 0. So it looks something like this. It's a little disjointed, so we'll just put some kind of dashed lines to connect these discrete segments. So something like this. Pretty straightforward. It's very much akin to first semester when you guys had position, velocity, and acceleration graphs, and you had to translate between those. The exact same process, the exact same physics, to be completely honest, except for this negative sign that you have to account for. Okay, so that's A completed. If a proton is released at x equals 5 meters, in which direction does this move? So we can do this entirely by inspection. So imagine we have a proton, it's positioned at x equals 5 meters. So what I'm going to do is go to x equals 5, and I'll put it right here on the potential surface. So this is, imagine this is a terrain or something like that, and we're viewing it from the side. You can imagine that this is a mountain, And maybe that this part here, this is a valley, that kind of thing. We're viewing it from the side. It's like terrain, kind of like geography, that kind of thing. We've put something that's a point, but it's round and it can, let's pretend it can roll. So anything with a positive charge, it rolls downhill. It kind of does exactly what you'd expect in like a conventional, we're just building up this analogy where we pretend that this is a geography problem or something like that, not a physics problem. Positive charges, they will roll downhill. So imagine you're on the side of a hill, you're in Halifax, you're on Citadel Hill, and you put a ball on the side of Citadel Hill and you let it go. It rolls downhill. That's what positive charges do. They roll down the potential surface. Negative charges basically do exactly the opposite. They roll uphill. They do kind of what is unconventional in your mind. The mental model you're building up, you have to kind of flip it. So what this means is this will roll down the potential surface. Well, where is down? Is down to the right or is down to the left? The potential surface decreases as we go to the left, so it's going to roll to the kind of to the left, so to speak. This is potential. The only real spatial coordinate we have is x, so it's going to move to positions of lower potential. That amounts to moving positions that have lower x's if we start at x equals 5. Lastly, we're asked, what is the speed of the proton when it reaches the edge of the graph? So this is what I was kind of getting at before. I kind of fumbled over, but I'm not sure if you guys had seen it before in lecture. It might be like 1 or 2 lectures in advance. So before we kind of wrote down a statement of conservation of energy, change in kinetic energy and the change in potential energy have to sum to 0. If this proton is released from rest, and it's going to start moving to the left, we can understand that it picks up some speed. If it starts at 0 kinetic energy, it may end up at some amount 1/2 mv squared. Now, the potential energy is, I don't want to write this. The potential energy change here can be equal to minus Q delta V, where delta V is the change in potential. Minus? No, it's not minus. It's positive. Sorry about that. So this is a way to calculate the potential energy here. If you guys haven't seen this, the potential of a point charge is equal to 1/2 Q over R, something like that. Imagine that you take QV, you have a second charge that you introduce. Q1 times Q2 divided by R, the distance between them. Suddenly this looks a lot like the potential energy, or perhaps you want to call it PE, whatever, that you guys are familiar with already. So this is very quick, like it's not really a proof, but it's just an example of a simple case that works. If you have not seen this before, charge times potential being equal to potential energy. If you have seen it, great. The explanation is not needed. But so what we have here is an equation we need to solve V. So V squared is equal to, we're going to move the second term over to the left and multiply it by 2 divided by m. Then we need to take the square root of all this. This looks a bit funny because we have a minus sign sticking out under the square root. But maybe I'm not going to put all the numbers in, but I'll expand this a little bit just to kind of convey that this is okay and kind of walk you one step closer to where you'd be ready to put an answer in your calculator. So what is this? This is the velocity. It's equal to the square root of minus 2. We have a proton, so the Q I'm going to replace with E, and that's positive E. No minus sign coming there. It's not an electron. What is delta V? Delta V is the change in potential. It's the potential difference from where we started, or where we ended up to where we started. So we're told this is moving to the edge of the graph. We know it's moving to the left. So what is the potential at the very edge of the graph? It's right here. It's 0. So this is kind of our final. This was our initial position. So we've ended up at 0. We started at 5 volts. So that changed -5. So you can replace delta V, if you're going to put this in your calculator, with -5 volts. And then we have the mass of a proton or whatever. The point here is that this minus and this minus, they multiply together and you have a totally positive quantity under the square root, which satisfies kind of the requirement that all the numbers here are real. We can't have minuses hanging out under the square root. But yeah, your first kind of demo and how you can really quickly solve these problems. You don't need to worry about fizz or anything like that. If you know what the potential is, you can multiply by the charge and you figure out the potential energy. Okay, so very similar problem. We don't have graphs this time. We kind of have a pictorial view, but another question on potential and potential surfaces, I guess, this time. So we're told to consider the equipotential contours drawn on the right. Charge Q1 has half the charge of Q2, and we're told that the units on these contour values, see there's little numbers associated with them. Those are the values of the potential along this contour in volts. First question we're asked is to draw in the electric field lines. So this is a little bit, I don't know, again, if you guys would have seen this in lecture. Hopefully you've seen this in lecture, which will make it my explanation kind of unnecessary or easy to understand because you've already seen it before. I think what you guys are familiar with is if you have a point charge, if it's positive, you can draw electric field lines. So not potential, but electric field lines. And they point radially outward, something like this. One of the rules of the electric potential that comes about from some of the calculus that you guys aren't responsible for is that the electric potential is always perpendicular to the electric field. So what this means, you can even kind of see it here because this diagram is accurate for point charges. Q1 and Q2 are point charges. You just had a point charge isolated in space. This line or this circle drawn here has constant electric value of electric potential all along the surface. If you move out further, there's a different value of the electric potential, but another circle somewhere along here, all the electric potential is the same all the way along here. It's a different value. Maybe it's 4 here and it's 3 here. You go a bit further out, the electric potential might diminish a bit further. Maybe it's only 1 here, but you get the idea of what these look like. To kind of circle back to the analogy that I built up on the previous page about how you can think of electric potential as kind of like a geography problem. So before I said, imagine that you had some terrain and you have a valley and you have a mountain, that kind of stuff, and you might put a proton here. It's a positive charge, so it rolls downhill. That's kind of a mental model you can build up in your head. Now, if this is kind of the side view of some terrain, if you want to get really artistic, I could even put like snow-capped mountains just to make this really hammer at home. Now imagine you took this view, which we're looking side on, and you look from the very top. So what people who make maps do is typically if you have a mountain that I had on the right here, when you're looking from the top, you can see kind of, there's the top of the mountain. And you can see here's a certain point further down that is lower height. Here's somewhere along here, lower height, but these are kind of same altitude is a way of thinking about it. And if you had a valley, it would be the same type of thing, except it goes into the page, whereas this mountain, so to speak, comes out of the page. So if this analogy isn't working for you guys, it's a pretty common one, and I think a lot of students like it once they can grasp it, but if it isn't working for you guys, don't worry too much about figuring it out. It's just, like I said, historically, it's very helpful for students. So we can compare what I've drawn here, what we have in the diagram above. So on the right, we have circles that are positive, right? We're told that this line here is 6 volts. This here is an equipotential surface. So everywhere along this circle is 4 volts, 2 volts. We're moving down and down and down. Now notice we're at 0. Again, if we're kind of, this is sea level perhaps, if we're kind of using this geography analogy, then we've gone to -2. So clearly this is a region of high potential right here at this point charge, and this is a region of low potential. So if you construct this model in your head, you can think if there's a positive charge, it will run from high to low. If there's a negative charge, it will run from low to high, that kind of thing. So just things you should be thinking of, and hopefully allows you to build up a model that you can understand. So one thing I told you, one of the rules, I guess, is that electric field lines are perpendicular to equipotential surfaces. I'm just going to use V because I'm lazy and I don't want to write out equipotential lines. We're just going to assume lines that describe the potential here, they're equipotential, they're perpendicular. The other thing is that the electric field lines, they go from high to low. If we know these two rules, we can basically annotate any equipotential diagram, any contours that we want. So part A wants us to draw these field lines in. I'm just going to follow these two rules and maybe erase this a little bit to tidy it up. But follow these two rules, and I think what you'll see is kind of very intuitive and sensible. So the first one I'll draw is straight across. Notice that at this intersection, this intersection, this intersection, I'm at 90 degrees, or the line I've drawn is at 90 degrees to the provided contours. And I start at high potential and I've gone to low potential. So I'm passing through the 6, then the 4, then the 0, then the -2, all kind of in that direction. And we can get similar type closed trajectories. If we kind of follow through, I'm going a bit faster and obviously not as neat. But you get diagrams like this. And like I said, I really hope you guys have seen something like this in lecture. Because these loops or these kind of paths, they just get bigger and bigger and bigger. Obviously, there could be one that goes all back here, comes in like this, and they're pretty symmetric. So there's, oops, I'm getting really sloppy. These are not perpendicular. Something like that. And we could add a couple arrows in really to label well where the lines are coming and going to. So those are our electric field lines. We can put infinitely many in, but just kind of having a good set that shows generally what the behavior is. So there's no need to draw, like you don't need to draw necessarily 4, you don't need to draw 10, you don't need to draw 12, just kind of enough to really show what's going on. It's subjective. Does Q1 have a positive or a negative charge? This is a region of high potential. The potential here is positive. Notice we have things surrounding it like 6 and 4. The potential of a point charge, if you want to reason it out with equations and not just concepts, is Q over R. The only way for this to be negative is if Q is negative. So the fact that this is surrounded by positive equipotentials kind of implies that this has to be a positive charge. The other way to look at this is we have a high potential, a positive charge would kind of roll away from it. While if it rolls away, think back to how we thought of electrostatic forces, that means there's a repulsion. So that's another way of coming to the conclusion that this is a positive charge. Or sorry, Q1, okay. I was making an argument for Q2. We flip everything we said. This is surrounded by negative potential lines. It attracts a positive charge, that kind of thing. So my mistake there. I was arguing for Q2. The argument is just the reverse of what it was. Okay. In what direction will an electron positioned exactly halfway between the two charges accelerate? So I've been talking this whole time about protons that will roll from Q1 to Q2. I think it's pretty easy to follow the logic that we've applied previously, that just electrons do the reverse because the charge is flipped. But the same, we could kind of, let's make a little space here, change colors to make things easier. We put in an electron. The electric field lines here, notice they point to the left. The force felt is equal to QE. So if this ends up being minus E times, I guess these are vectors. So this minus sign right here implies that if the force is to the left, which follow, or sorry, the electric field is to the left, the force is to the right. Or in other words, negative charges roll up a potential surface. That's kind of a way to think about it as well. Hopefully clear though from a couple different angles. Part D is suppose these are 8 meters apart and that the 2-volt contour line, which is this one where we put the electron, runs exactly halfway between them. What is the charge on Q1? So we have to do a little bit of algebra. We have to use the equation that we wrote down here. So the really nice thing about, like I said before about potentials, is that they're just scalar quantities, and when you have scalar quantities, they just add. So kind of the potential, let's just call it at, I don't know, wherever V is equal to 2 volts, that's kind of circular, but let's ignore it. So at that point in the middle, it's just equal to the potential from charge 1 plus the potential from charge 2. We don't have to worry about how they combine in different angles, and is it a perfectly straight line between, or a perfectly horizontal line between them, or is there some sort of Y component and X component that we have to consider? None of that. We just get to add them up. It's super straightforward. So we know that this is equal to 2 volts, so we'll keep this in mind, and I'll just write V on the next line, and we'll remember that that means 2 volts. That's this contour line that we're solving for. Okay, so John said that was a bit too easy. What just happened? I claimed that potentials make things very easy, so without a bit more something specific, I can go over it, but I think basically we started doing work in potentials, and potentials make things very easy. So I guess what I'm getting at is suppose there was a charge over here, suppose there was a charge over here. We'll call this one A, we'll call this one B. This might make an electric field that points like this. They're both positive, and this one kind of at this point right here. And this one, I don't know, something like this. This is the electric field due to B. So to figure this out, if you wanted like what is net electric charge at this point, you would take this, you kind of do the vector addition, tip to tail, that kind of stuff. You'd have A, you'd have B, and then you'd say, okay, this is my resultant vector, or something like this over here. That's not a great vector addition, but you'd have to worry about things like that. This is because these are vector quantities. With potentials, it doesn't matter. So I guess maybe we do a side-on drawing. I really like the mountain and valley kind of analogy. So if we're side-on, imagine that you took a mountain and you just drew it here. And suppose that you said that this is 10 meters, this height above sea level. And then entirely separately, you have a valley, something like this. And this point here was 10 meters below sea level. So this is fine. They're two separate features, that kind of thing. But now imagine that you kind of superimpose them. So this one's here, and this one's here. Now I did a really bad job drawing this. Let's pretend these are aligned, and this is here. So the net contour that you would get out of this would end up with something like this over here, But then things are a little bit weird over here, and this point that we were worried about ends up at 0 because plus minus 10, they don't work like that. Actually, forget this analogy for a second because this is my drawing skills are letting me down and not letting me explain it well. This is like superposition of waves, basically. You have the amplitude from one wave, superimposes with the amplitude from another wave. If they're in phase, out of phase, they just straight up add together. That's why this is so easy. It just adds together. Potential is a scalar quantity, amplitude is a scalar quantity, that kind of thing. So what I'm arguing in this case, and hopefully this resolves your question, is that these contour lines here, they're not perfect circles, notice. It's a perfect circle where the charge is, then there's some skew. They become kind of like ovals. And the reason they're not perfect circles is because the contour lines that are kind of, oh my God, these drawings are so bad, I'm sorry. Yeah, okay, this is a better profile of V versus X for our situation up here. So these aren't perfect, especially in this region kind of from here to here, because some of the circles that would originally be here from Q2 in the absence of Q1 are interfering a little bit with the shape of the circles of Q1 in the absence of Q2. They're kind of overlapping, which is why we don't have perfect circles around them. We have these squished oval shapes. So what I was getting at before is that if we want to, basically what we're trying to do, maybe this notation here made it a bit more complicated. So the question for D says this line here is exactly in between these two spheres. So this is 4 meters here, and there's 4 meters as well on the other side. And it ends up being 2 volts. What is the charge? So what I'm saying, I guess, is that this line where we ended up at 2 volts, there's a contribution from charge 1, there's a contribution from charge 2. We arrive at 2 volts. There's no directions, nothing like that. I imagine that may have been overcomplicated because I went very circular, but yeah, maybe by the end when I just wrote it down with 2 volts instead of a function or something like that, it became a little bit more clear. So personally, I find these topics are a little challenging to describe because they're a little bit more abstract and just people think in different ways. So it can be hard to verbalize the picture you have in your own head, and it can be hard to if my picture doesn't overlap with your picture. So it's challenging, but that's why we're here and talking about all this. Okay, so we have contributions from the two different point charges. We wrote on the previous slide what those potentials are. So we just have Q1 divided by R1, and these are all scalars, no vector quantities in here, so this R is just a distance. And we have nearly the same thing for the second charge. Right, so I can maybe squeeze out one more line before I have to erase this ugly red diagram. The two things we need to keep in mind, this 2 volt line is halfway. So remember what I said, it's kind of 4 meters on either side. So I'm going to say that R1 is equal to R2. We're just going to call it R, and we know that this is equal to 4 meters because that's the distance to the 2 volt line going across the middle from either charge. The other thing is that we have this detail right here. Q1 is half of Q2 in terms of just the magnitude of charge. Obviously, we said that Q1 is negative, Q2 is positive. But what we have is Q1 is equal to 1/2 or minus 1/2 Q2. And just to make things a little bit easier, what are we looking for? We're looking for Q1. Yeah, okay. We need to solve this for Q2 to make things a little easier. Q2 is equal to minus 2Q1. So what I'm going to do is I'm going to sub in R, and I'm going to sub in this in the above line, but I need space. Okay, so let's sub that in, our 2-volt line that we're trying to solve for. We can even factor array the 4 pi epsilon naught out. Q1 is still Q1. It's divided by R now. And we have a minus that we've picked up, and Q2 becomes 2Q1 divided by R. So let's factor a little bit more. Okay, so we have all of our kind of constants there, Q1. And what we're left with is 1 minus 2, or in other words, minus 1. So Q1 is equal to minus 4 pi epsilon naught R times 2 volts. And we had that minus sign out here. We knew that Q1 was supposed to be minus, so I think we're all set. So that's the answer right there. Okay, so I think that's all I have for these questions. I know these were a little bit, maybe some of the explanations were a little bit fuzzy. What I'll do, if anyone wants to stick around, there's no obligation to stick around. We'll go back and we'll talk about the units in the first question, see where I made a mistake perhaps. But before we do that, I'd rather make sure that we get any questions that have come up throughout. So let's do that. Maybe we'll wait a couple seconds for questions, and if anyone wants to stay, we'll go back here and figure out what the heck was going on. Okay, seems like why is Q1 is 1. Why is Q1 1? I assume you mean on this one, so let's go back here. So what I think probably what you're referring to is where that 1 came from. Correct me if I'm wrong, but I think that's what you're getting at. Okay, awesome. Yeah, so what I did was I actually ended up factoring out Q1 over R from both of these terms. So yeah, so the Q1 actually came out here from both of them, and the R was put into the denominator over here because there's a common Q1 and QR in both. But there was this factor of 2 hanging around that was in the term that we originally labeled Q2. So that's, I guess, where it came from. It's like the amount of Q1 over R that I removed from the first term was 1 amount, and the amount of Q1 over R that I removed from the second term, there was 2 amounts there. Just simple, straight up factoring. And that came about from when we wrote over here what the relationship was between Q2 and Q1 based on the details from the problem that we had. One is half the charge of Q2. So hopefully that's a little bit more clear now. Oh, did Alex just solve everything for me? Okay, so I think Alex has our final, the problem to the thing I wanted to get up above. Shiraz has a question. Yeah, why is the electric potential 0 while the electric field is not? I think you mean probably for the last question as well. Perhaps it's, to answer your question, it's actually better to consider this one, if I'm correct. So this kind of talks, this question here has a little bit more about the origin of the electric field kind of from a visual and a mathematical definition. So it's just the slope, which we've defined here. So electric field is the slope of the potential. So when we have a graph of potential to get to the electric field, what we did, if you recall, is we found the slope. Um, so to answer your question, you can think of many situations, right, where like right here, for instance, the potential is 0, um, but the slope is non-zero. So you can have a non-zero electric field when you have a non-zero electric field when you have a 0 potential. So the way to think of potential is just like uh, what sort of altitude is what I'm looking for. It's just like how far up or down this surface are you? So you can see that's a very easy example there of why, like, where the electric potential is instantaneously 0 in this graph at around x equal 4. If you flip it on its head and you consider, is there a case you can have the electric field be 0 but have the electric potential be non-zero? That's a little bit more interesting, because the other thing that we kind of do, first I'll answer the first part. If we want to figure out what the electric potential is, we have to integrate this time. So it's E, technically we're going to do this properly, vector E dotted with dx. So it's the amount that you move. It's kind of like taking the area under the curve when you're trying to figure out, you have an acceleration curve, how much did your velocity change? To calculate the area under the curve. Same idea. But the thing that we have to keep in mind in a lot of these problems, potential isn't really that important. Potential difference is important. So what this really means is we're calculating a potential difference, and you will start at kind of an x initial and an x final. And because this is a definite integral, you really only get the difference. And sometimes because you only get the difference, if you want to convert to an absolute, you have to give it some sort of, you'll get like delta v as a function of xi and xf, but you'll have some sort of v naught that you basically can move down depending on the context of the problem. But like I said, this is unimportant. The difference is really the only thing that matters. And I think, just to read the question and kind of drive it home, the main point is that if you think of things as a slope, you can think electric field, you can have a slope when things are at 0. Pretty straightforward. Yeah, exactly. The absolute potential or the instantaneous potential is kind of sometimes it's useful, but it's not really that in the real world. It's something that most people talk about. Okay, so before I drone on for too long, I think Alex has given me a free out, and while I've been chatting with you guys, I pulled it up on my phone. So I had an error right here. So when we were doing the unit analysis on here, I forgot a factor of a meter, and I was unhappy because we didn't have enough per meter. So what would happen here if we had the -3? We'd be left with meters squared there. We'd have amp second meter squared. That's a coulomb per meter squared, which everything comes out nicely. So if you guys want to revisit that, the key thing is get on your own, actually get the units on the constant right, unlike I did. Thankfully, that means my problem solving skills were not the weak link in this one, and thanks to Alex for doing the heavy lifting of getting us to where we need to be and making my life easier. Cool. I'm glad you guys hung around, and hopefully it wasn't too difficult to follow. Like I say, some of these topics are a little bit, I think that the equation side of things is pretty straightforward and that kind of thing. But if you're trying to build up a mental model or trying to visualize things, it gets a little distracted nearing the end of the year.